Thank you very much, Carrie. I'm very pleased to be here. I hope this is going to be a lot of fun, and I will be open for questions, especially afterwards. And if anybody wants to contact me, I've got my information. I do have my website and email, and I'm sure Carrie could also provide you with some of that information. Carrie's right. I just finished up doing a class for the Chicago Public Defender's Office. It was a bunch of lawyers. And one of the principal topics they wanted me to talk about was Shotspotter. And that's what I spoke up and said, gee, I just studied that and gave a class, which included that information. So I'm going to give you a lot of that same information here. And then I'm going to talk about a case, actually an analysis that I just finished up that was very exciting for me. And I'd like to share some of that with you, an actual forensic analysis. So what I'm going to do today is talk about multiple microphone systems and how the audio from those microphones can be used in a forensic audio analysis. So there's really about 5 questions that I'm going to talk about. Can we detect and recognize a sound? Can we determine the direction to the source? Can we locate the source? And then a couple of extra things, and this goes in with my analysis I just finished up. Can we associate multiple sound events and discriminate between multiple sounds? Okay, there's a lot of other things you can do with multiple microphones. You can do sound enhancement, you can do beamforming, but all those things are probably subjects for other interesting talks. So I'm going to limit myself to these 5 questions. But before we begin, I need to talk a little bit about acoustic sound propagation, okay? Because that's really critical to everything that we're doing. So we have a point source represented by this little red dot, okay? Sound will propagate outward spherically from that point. And it has a spherical spreading loss of 6 dB per doubling of the distance. That means that the amplitude is 1/2 every time you double the distance. That wave can be considered a plane wave in the far field. You can see here in the near field, the wave is very curved, okay, and it doesn't look like a straight line. But as you get out toward the far field, it's starting to look more and more like a plane, like a straight line here. So we can take advantage of that knowledge. And that's a lot of what we're going to wind up talking about here in this analysis. The other thing that's very important is that these waves travel at the speed of sound. And speed of sound primarily depends upon the temperature. To a lesser degree, it depends upon the barometric pressure and the humidity, so we usually ignore that. I very commonly have to go back and look at what is the temperature that a crime was committed in a particular area on this date at this time. So that is one of the interesting things that you commonly have to do in audio forensics. Humans can detect the direction of sound. How many? Well, normally I would ask everybody to raise your hands if you've ever played Marco Polo, but I'm just going to assume that everybody's done that at some time. So you're familiar that humans can figure out, where a sound is coming from. So how do we do that? Well, if it is a high frequency sound, those high frequencies don't diffract around your head very well. They get attenuated. And our brain uses what's called interaural level differences. And depending on, if sound is louder in one ear than the other, we get a sense of direction. What happens with low frequencies? Well, low frequencies will diffract around your head. there won't be much of a level difference, and our brain automatically does time differences. So that way we're actually able to cover both low frequencies and high frequencies, and our brain just automatically, figures all that out. And as you know from playing Marco Polo, we can get a general sense, but we don't do actually very well with it. So as engineers and scientists, we're always trying to augment or improve our ability to, to locate a sound. Well, we used to use, a lot of mechanical devices, but these days we have more things at our disposal, like arrays of microphones, and we can use the time difference of arrival between those. So if I have a sound source and I have these waves propagating out from it, and when those waves strike a microphone array, it's going to hit different microphones at different times. And depending on those times, and if we know the orientation of our microphones, we can calculate the direction back to the source. If we have a widespread placement of microphones, we can use multilateration and actually locate and know where that source was, not just the direction to the source. Now, some of the requirements here, and I'm gonna belabor this point, is we have to know the precise locations of the receivers, and they all have to be time synchronized in order to do that. But we can actually get very, very precise locations and angles of arrivals if we can meet these conditions. So let's talk about Shotspotter. Shotspotter is probably the best known gunshot detection system around. What it is a grid of microphones that are spatially distributed around a city, okay? They're typically, like blocks apart, and they can be on poles or they can be on buildings. They're typically sensitive. They can detect gunshots for over a mile. When they detect, they try to recognize that it is a gunshot and not another similar sound. And they then try to locate it. And when they do, they send the GPS coordinates to EMS. And, in their studies, they say they're accurate to within 25 feet. And they've got installations in over 100 cities, including Chicago. And for anybody here in Central Texas or in Austin, the software that originally was used to develop Shotspotter was, I think, based on LabVIEW from National Instruments, which is headquartered here in Austin. Just a little fun fact. The Shotspotter process is a gun is fired, Shotspotter detects it and attempts to locate it, and they claim a 90% probability of detection. They don't say what the false alarm rate is. When they have a detection and a location, they send it to their incident review center, and they can send an alert within 60 seconds to the police. And the police typically will respond and go to that location and see what was going on. They claim to have 15 million acoustic events, gunshot-like events. And for every detected shooting, they produce a detailed forensic report. And if you go to their website, you can actually find it there and download it. So it's just a lot of kind of interesting stuff about them. One of the things I did for the Public Defender's Office in Chicago is I read a couple of field evaluation reports, one from the year 2000 from the Department of Justice, and they found it had an 84% probability of detection and was able to locate accurately within a 41-foot error. And then in 2019, I found that the National Institute of Justice did a field test, And they found 80% of the shots were detected and 72% were triangulated within a 25-foot margin of error. So, these are different tests that are done. How meaningful are they? Well, everything depends upon all the reflections and, all the other acoustic properties. Excuse me, living here in Central Texas, we have a lot of cedar pollen out right now. So I may have to take a sip of water every once in a while. So as I was saying, you do have to take into account a lot of acoustic propagation whenever you take a look at statistics. So how does Shotspotter work? I actually don't know precisely what they do, but about 10 years ago, I was sitting at a conference table and one of the Shotspotter algorithm designers was there talking about it. And I had a nice discussion with him. And from reading some of my reports, I'm going to give you a fairly good idea as to, what they most likely were doing. And I say were because I don't know if they've moved on to deep learning techniques or not. I have not heard anything. So I'm going to talk about the typical parameters that, that one would try to extract for a gunshot. We have temporal parameters. So over here on the right-hand side at the top, I've got a model of a gunshot impulse. And right below it is an actual recorded gunshot sound. And you can see that, the actual ones are a lot noisier, doesn't exactly look like the theoretical model. But this is actually one of the better ones. So, there's a lot of difficulty in making measurements, but some of the measurements include the peak amplitude, the rise time, because it's close to instantaneous, and that's a good way to discriminate from other sounds. Look and see whether it's skewed, what the kurtosis is, measure the pulse length, which is typically, what you might consider to be one cycle. And the pulse width is really just the positive phase duration, and maybe something like the decay time constant. So those are nice theoretical things, but when you apply it to real signals, it sometimes gets kind of messy and noisy making these measurements. The other way they like to make measurements is in the spectral domain, and look at spectral energy features, which might include ratios of the energy in different bands, maybe compute the spectral centroid, the skew, the kurtosis. Again, my red plot over here is the theoretical spectrum of a gunshot, and down below is one of the nicer spectrums of a gunshot. Typically, they're really noisy. There's a lot of other stuff going on in there. So, any type of measurement that you make, they're typically going to be noisy and kind of messy. The nice thing about Shotspotter is that they know all the characteristics of their microphones. So once you've detected it, you try to classify it and determine, is it a gunshot? And I don't know what kind of classifier. Again, they may have moved on to deep learning techniques. But let's assume that we've detected and we've determined that it is a gunshot. So Shotspotter then will say, we're going to try and locate it. So there are several measurements that they can make. The first thing is that they will get the GPS time of arrival for each one of the sensors. And from that, they can compute the time difference of arrival. Then they might look at the GPS accuracy related to the number of satellites. They'll try and compute the source location and the error ellipse, related to that location. Try and compute the elevation and also the elevation error. And all of those things go into, the confidence, in any of these estimates. And they use all of that information to say, are we going to send this on to EMS and on to the police? So their decision process is it a gunshot? Well, is it a gunshot-like event that we detect? Then if it's detected, you look and see, is it a gunshot? Are there multiple related events? Because typically if there's one gunshot, there's likely to be more than one. And hopefully it's not like a helicopter where you get many, kind of shockwave looking events. And finally, they try to localize it and compute the error. So that's kind of what I've heard and what I've read is their likely process. So once you get these time differences of arrival, how do you actually locate something? So there is a way, if you have these time differences and if you know where all the sensors are, you can compute you can compute these hyperbolas. And this is the standard localization technique for these kinds of arrays. These widely distributed, spatial arrays of microphones. So what they do is they take a pair of sensors and they know the distance between those sensors and they have the time difference of arrival, okay, from any event. So when any sensor detects something and they can get the actual time from the GPS, then they can compute the time difference between those two sensors. Well, it turns out that you can locate that source somewhere along a hyperbola, okay? And that hyperbola defines where these time differences are all the same, okay? So if you have this time difference of arrival between these two sensors, you can compute the hyperbola of constant time differences. And I'm not going to go through all the math and all the equations, but I do want to point out that Professor Rob Mayer has a very nice description of all of this in his book, Principles of Forensic Audio Analysis. And unfortunately, Rob couldn't be here. However, he told me he will listen to the recording. But if you are really interested, please check out his book, or you can write me and I do have more information on this. So I did a little example, and I actually work in radio frequency a lot. So I did this one, using microseconds, but really think of it in milliseconds. If I have two receivers and there is an event that happens, that event could happen, the source could be anywhere along this blue line, okay? And as you can see, we have a time of 16 over here and a time going to receiver 2 of 6, and the time difference is 10, okay, for this receiver. And for the bottom receiver, the time to receiver 1 is 17, the time to receiver 2 is 7, and again, the time difference is 10, just like the one up on top, and that defines this hyperbola. So once you've computed these hyperbola, okay, what do? So there is a minimum layout, and you need at least 3 or more receivers in order to find a unique location. Okay, so if I have 3 receivers and I can compute these hyperbola, they're not going to intersect at the exact same point, but you want to find the minimum area of intersection. And that minimum area is that error ellipse. So how do you find that? Okay. Oh, and we also need to compute the error, okay? Error is always very important whenever you're trying to estimate something. And that gives you an idea as to how good that estimate is. So most people have heard of triangulation, okay? But triangulation means that you know some angles to your points. Well, we don't have any angles here. What we have, the only thing that we can measure is the time difference of arrival. So we have to use a technique called multilateration. And you guys can look that up and compare that to triangulation if you want. But what you wind up doing is you have to compute these range estimates. And you can set up your equations, and I'm not going to show you what they are here. But I will tell you that there is no closed form solution. And that solution surface is non-convex, which means that you've got to, once you have all of your equations set up, you have to go to your favorite MATLAB or Python or whatever language and get your favorite optimization routine, like iterative least squares or gradient descent algorithms or whatever, and you can converge to the best possible solution. And if anybody's interested, I have a reference down here that gives you all the theory for all of these different techniques. So that is, let me see. Yeah, that's kind of what I think Shotspotter does. Okay, so they get these time differences of arrival to all of their sensors. They know where those sensors are. They compute these hyperbola for every sensor pair, and then they do some kind of iterative optimization to try and find the best intersecting point for all those hyperbola. So that right there, I think, is Shotspotter. There is another technique to try and find the intersection, and this is the approach I used about 10 years ago, is the spherical approach where I put a sphere instead of a hyperbola and tried to find the intersection. So a sphere about each one of the receivers. And with a lot of math and a lot of variable substitution, I was able to come up with solve a matrix. And that actually did have a closed form solution to that set of equations. So if anyone is really interested in a closed form solution, I think that book, the one by Donahoe, talks about it. It doesn't really give that solution. I actually did that at one point. So, but it was a lot of work, but it can be done. So that's kind of how you locate, a source from a distributed array. I want to talk just very briefly about how you can find the direction of that source. So if we have a wavefront, and that wavefront is moving through an array, it's going to happen at a particular angle. And by doing, again, time differences of arrival, you can estimate that angle. And I've got a couple of examples here of, you're really looking for this theta and this cosine theta. And the distance between your any pair of microphones and the speed of sound and cosine theta will give you your measured time difference. Okay, and that's the thing that you get off your data. And what you want to go back and your distances. Hopefully you know your your distances. You hopefully know the speed of sound, and what you want to do is to estimate your angle, because that angle is going to be the angle back to that particular source. So I've got an array of actually 5 microphones here. And this is a demo I used to give to students over at the University of Texas at Austin, and sometimes to high school students. I have something that runs in real time, and they can go around and clap their hands, and actually it will point at them and things like that. So unfortunately, I can't do that for you guys. Can't give you nice real-time demos. But what you wind up doing is you compute your distances, you get your measured time differences of arrival, and you can form a matrix, and then you can solve that matrix for your X, Y, and Z there, which is really your cosine thetas. Then you can solve that for your theta, which is your angle back to the source. Okay, so I'm going to conclude this section on gunshot localization. So you can use a large array of spatially distributed microphones to locate a gunshot source. And that's what I think Shotspotter, uses a hyperbolic geolocation with an iterative solution. Also, you can use arrays to find the angle of arrival to that source. And there's a lot of like sniper locators using small arrays. And I've actually worked on those quite a bit as well. But you can only do that if and only if you know the microphone locations precisely, and if they're all precisely time synchronized. Well, what happens if you don't meet those conditions? Can you do anything? So this is the forensic cases that I typically get. Okay, that's where you've got multiple microphones. They may be, police body cams, dash cams on the cars, bystanders with cell phones, and lately, I've been getting live streaming. And you don't know exactly where any of these microphones are, and they are certainly not time synchronized in any way. So what can you do? Is it possible to associate multiple events from any one source? And can you discriminate among multiple sources? And because a lot of these are gunshots, they're typically, saturating your amplifiers, and you can't really tell them apart by looking at them. So what can you do? So I've actually worked 3 analysis or cases. The first one that I got was National Geographic Conspiracy Busters. That is a show that they still haven't aired, but I'm hoping someday they will. And they asked me to analyze the ABC, CBS, and NBC recordings of the 1981 Ronald Reagan assassination attempt and determine if there was a second shooter. So again, we have 3 microphones. You don't know exactly where they are, and they're certainly not time synchronized. Just last month, they finally concluded a case up in Dallas that was a police shooting. Professor Rob Mayer and I actually worked on this case. And I was able to determine the order of shooting and who fired first using this technique that I'm going to show you. And just October, I was contacted by the Washington Post and asked to analyze multiple live stream recordings of the events surrounding the Kyle Rittenhouse shootings. So, and there I had to go with this technique that I'm going to talk about. So I'm going to show you guys a whole lot of math, and you don't need to pay a lot of attention to the math, but I'm going to try and explain it quickly. This is all from my paper that I gave at the AES International Conference on Audio Forensics in 2019. So I'm going to run through this real quickly for you guys. So don't get put off by the math. So first of all, we'd like to know, can we locate the source if everything is unsynchronized? okay? Even if you know where the receivers are, and typically you don't, but assume you do, but they're not synchronized, is it possible to locate the source? So if we start out by looking at the distance from the source to the receiver, we can get an equation. And we come up with an expression for the time of arrival from one source to one receiver. And this particular expression here that you see is really the basis of how I was able to solve this particular problem and come up with the proof. So you'll probably see that equation again. So once you have that equation, you can calculate the time difference of arrival between two sources at one receiver, and for those same sources at a different receiver. And if you subtract those, you wind up with an expression that you could then solve for the source location. And unfortunately, you can't solve it. Okay, there are probably an infinite number of solutions to that, which says that you can't get your source location. And that's exactly what I was trying to do for a couple of these cases. And then I discovered that there were things, however, that I could do. So this is the basis of my paper, is this one particular equation, the time of arrival from one source at one receiver. And I'm going to then compute the time offset from an event from one source, okay, and a different event from the same source. And I will look at the time differences of arrival at two different receivers. And lo and behold, if I subtract those off, they wind up being exactly the same, okay, from two different receivers, okay, even though they are not synchronized. So what that means is that these time differences, and you can measure them, okay, from your data between multiple events from a single source, and as measured at different receivers, is always the same, okay? Assuming that the receivers are not synchronized, and you don't have to know the locations of the source or the receiver. And I'll add one more thing, that the receivers should not be collinear, okay? So if they're spatially distributed, you can identify multiple sounds from the same source. Now, I also figured out that you can distinguish multiple sources. So I can again look at these time offsets from different events from different sources, looking at them at different receivers, and lo and behold, part of these expressions are the same, but part of them are different. And what that means is that these time differences of arrival that you can measure, generated by different sources, will be different at different receivers. Okay, that means you can distinguish them. So I gave you all the theory, and hopefully I didn't scare anybody. So I'm going to, first of all, give you a simulated example of what that all means. So I've set up a simulation layout in the upper left. I've got three receivers, R1, R2, and R3, and I've got two sources, S1 and S2. And then I have each one of those sources providing an output, you know, what I'll call an acoustic event at different times. And I plotted when each one of those receivers receives each one of those events from those sources. And as you can see, it actually looks like kind of a mess, even though I have everything, you know, simulated, and I have different symbols for everything. So you can see where they are, but if you didn't know what they were, you would not be able to figure it out. And it's even worse if you look at the analyst view, because the analyst has to time align something and they typically choose the first one, and everything is actually, different events, or actually different sources appear first, depending on where these receivers are. And sometimes you even get things that are overlapping. So what can you do? Well, my paper says that you can shift these things around and you're going to get things that line up. Okay, if you think about it, it actually makes sense, but this is a nice proof that you can align the events, okay, from different recorders. And if they're from the same source at the same location, they'll all time align. So the top one shows that I'm aligning all the events from source one. And then by shifting them differently, I can align all the events from source two. Okay, so now that we have the theory and we've seen that it works in a simulation, can we apply it in a real case? So back in August 25 of last year in Kenosha, Wisconsin, we had Kyle Rittenhouse was at a service station at 63rd and Sheridan, and he had an AR-15 assault rifle with him. And he was standing around outside that service station, and a gunshot could be heard, and someone rushed toward Rittenhouse. And about 2.5 seconds later, he turned and he shot 4 times, killing the rusher. He circled around the back of the car and more gunshots could be heard. And he finally left the scene and he walked along Sheridan and he shoots and kills somebody else. So there's a lot of stuff going on here. But what Kyle Rittenhouse claimed was that he did not fire that first shot. Someone else did. And he got so frightened that he started shooting himself. So the Washington Post contacted me and they asked, could I determine if Kyle Rittenhouse fired that first shot? So what they had was a number of live stream videos, and I was able to extract the audios, but I have a couple of screenshots from the live stream videos. On the left-hand side is a cell phone that is in front of the service station. And on the right-hand side at the bottom is one off to the side. And you can actually see Rittenhouse over there. And I chose this particular frame because there's one frame that has a possible muzzle flash in there. So that is kind of important. So the Washington Post actually had 5 live stream recordings in that area. There were, and I've got a map here along Sheridan, and kind of at the bottom, for some reason my pointer's not working. Oh, well, I'm not quite ready for that. Okay, I've got a map here, and at the bottom of the map is an area in black. And the red with the KR, that's Kyle Rittenhouse. That's his location where he was. And I have a cell phone at location DC and another cell phone at location REGG. And up at the top, a couple of blocks away, there were 2 more cell phones called Troy and Rundown. So I was able to extract the audio and start analyzing these. And just to give you a little more context here, I blew up that area, the little black area. So you can see the service station, you can see where Kyle Rittenhouse was. You can see another potential shooter at location Z, which I did not know until the end of my analysis. And a couple of other, the DC cell phone, the Reg cell phone, and later, again, at the end of my analysis, we found another live stream recording at location NP. So one of the first things that I did was I wanted to look at the audio and take a look at these gunshots and see, did they look similar? So the question is shot one from, did Kyle Rittenhouse shoot shot number one? We know he did shots 2 through 5. So I looked at shot one from the recordings from several blocks away because they were not, heavily distorted. They're actually fairly clean signatures. And, if I just look at especially the red on shot 1, shot 2, and shot 5, they all look really similar. And then I look at their spectra, and especially the red one had a peak around 200 hertz. So my first thought is that could have been Kyle Rittenhouse, did the first shot. The other interesting thing, because you guys are all audio folk, is that there's a big spectral difference between those two recordings, even though they're actually very close by. So I assume that the blue spectra has a high pass filter. And again, why am I interested in that? Well, it's just that it's difficult to make comparisons, between different recordings if they have very different filtering. And that's one of the issues that us forensic guys always have to deal with, is we usually don't know. We don't have access to the recorder, and we don't know what cell phone it is, so we can look things up. So I just found that very interesting. So at this point, I'm thinking that, yeah, it could be Kyle Rittenhouse did the first shot. And I got the Washington Post was very interested. Then I said, okay, I have this technique that I wrote a paper on, so I'm going to try to line these up. So I lined them up, and we knew that the shot number 2 through 5, okay, shown here in the middle section, we're all Kyle Rittenhouse, because you can watch him in the video, and it looks like he's doing all the shooting. And it turns out that, sure enough, if you align everything to that shot number 2 that I've labeled S1G4, that's the first shot in the group of 4, everything looks like it lines up. Okay, so that 4 in the middle line up. The last 3 at the end look like they line up. And in fact, that very first shot at the left, I've got these red stripes, and that they all look like they line up. Okay, but the problem is that these are all, a lot of these are almost collinear. So I asked Washington Post, and they searched around, and they actually found another live stream that was at a very different location, the one I called NP, that was down at the bottom. And I was able to analyze the 3 that I put. Let me go back and show that. Yeah, the 3 black ones over on the left-hand side. And unfortunately, I still can't, oh, there's my cursor. It's just being very slow. I don't know if you guys can see that. It's not working good. But the DC, the Reg, and the NP are the 3 that I'm going to analyze. And as you can see there, they form a nice spatially distributed array of receivers. So I went back and I just analyzed those 3, and I lined up that group of 4, and they all align almost exactly. Okay, there's maybe a little bit of movement, people are walking and stuff, but that's within a 1 second time period, and they all line up very, very closely. So I think my technique right there proves that those are all fired by Kyle Rittenhouse. Then I went and I looked at that first shot, and the top plot there shows, that first shot from the daily caller. The middle one is from the reg, and the bottom one is from the NP. And the first two plots are pretty close, but they're not exact. But that last one is really different. So at that point, I'm pretty sure that it was that first shot was fired from a very different location. And I also was looking at the first reflections, okay, because I found things that looked like they were some pretty good reflections in there. So I went back and I gridded the location. So I put some white dot, a little grid in there, and I located all of my sources and all of my recorders. I got the locations in that grid, and I used Google Earth to make measurements between all of those sources and receivers. I also looked up the approximate temperature so that I could look at the speed of sound. And I made a model. And there's my grid, and I have my 3 receivers and my 2 sources. And I have on the left-hand side, and on the right-hand side, I have my measured event times, okay? So then I went and I aligned them up according to the shot number 2 that we know is the Rittenhouse shot. And it turns out that I only showed the first 2 in that group, and they are perfectly aligned. But if you look over on the left-hand side, they don't look like they align very well, okay? And that's what we showed. And my model showed almost the exact same things, because I'm interested to know if the location of that other shooter is a good location. So it looks like my model, I can't use math to determine it, but if I can use other techniques, I can look and see, is it consistent? So I went back and I zoomed in heavily, and it turns out that my model is actually very, very close to my measured. So that tells me that this is from a different location from the Rittenhouse shooting. So it's probably a second shooter, or I should say a different shooter at a different location. And my model is actually pretty good. So I think I know where that other shooter is. And the other thing that I did is I went back and I did a complete kind of a ray tracing analysis of the reflections. And I went and compared those all to my measurements that I made of all of my reflections. And it turns out that very, very close. So that gave me a lot of confidence of where that other shooter was relative to where Rittenhouse was and all of my receivers. So in conclusion, my timing analysis proved that shot number 1 emanated from a different location from shot 2. And we know that shot 2 was Rittenhouse. The locations in my model were consistent with the measured gunshot timing. The locations were also consistent with my reflection analysis. And from all of that, we can conclude that Kyle Rittenhouse did not fire the first shot. So the end result of all of that was, the Washington Post had gotten really interested when they thought that that Kyle Rittenhouse did fire the first shot. But when I was able to prove that he didn't, they were calling me night and day for about 2 weeks. And when it came out that, no, we can prove it wasn't, they said, oh, thank you very much. Goodbye. And that was the last I heard of them. So it was a very exciting 2 weeks of my life, night and day, trying to get this analysis done using a paper that I had just recently published. So anyway, that concludes my talk.